Hey there, Physics 131. Let's look at the reading today. So we're now into chapter 11, which is the last chapter of this course. And just to let you know, for Physics 132 in January, Professor Harlick is going to start up with chapter 17 on electric charge, force, and energy. So getting into electricity and magnetism. But here we are, we're just going to talk about waves. And it starts off with a picture of a bat. And the idea is that bats have this chirping sound, but we don't hear it because it's ultrasound. So let's start in with waves. And so today we're going to start with wave pulses and just wave motion. So basically, if there is some sort of disturbance in a medium, you can get energy traveling outward. For example, this little cylinder hitting the surface of water. We can think of water waves as moving along. Also, if you shake a rope, you might get a kind of a pulse which goes along that rope. So we talk about wave motion. It's a disturbance produced by some vibrating object. So this kind of links you back to chapter 10. The disturbance moves through a medium and causes points in the medium to vibrate. When the disturbed medium is a physical material, the wave is called a mechanical wave. And so this beach ball hitting the water, you can imagine these what are called wave fronts. They expand out circularly, but as viewed from the side, there'd be these little bumps that would move outward at some kind of speed. There are two kinds of waves. There's what's called a longitudinal wave and a transverse wave. So a transverse wave is sort of what we're a little more used to. You vibrate the medium in one direction, and then the waves propagate in a perpendicular direction. So the x-axis here shows the direction that the wave energy moves, and the y-axis shows the vibration of the string there. But there is something called longitudinal, where you have them both parallel. So you can shake or vibrate a slinky, for example, along its length, and then there can be these waves of compression and decompression that move along the slinky, and that's called a longitudinal wave. So basically, longitudinal wave is one in which the vibrational motion of the particles is parallel to the direction of the propagation of the disturbance, and a transverse wave, the vibrational motion is perpendicular to the direction of the propagation of the disturbance. Waves can be reflected off of a wall, for example. If the rope is tied to a solid wall, then when a pulse hits it, it'll be inverted on reflection. If it's tied to a free end, which is allowed to oscillate up and down, then you can get a not inverted pulse that gets reflected back. And lastly, it introduces sound waves. A sound wave can be produced when you have vibrations that you can actually hear, and it turns out that sound is a longitudinal wave in the air. In section 11.2, the idea here is we have a very specific vibration starting a wave, and that is simple harmonic motion, which we did in chapter 10. So if that happens, then you get a wave, which, so here's something, a position versus time graph of maybe the end of a wave, then that'll send like a cosine shaped wave along the particle or along the medium. So there is one end of it, simple harmonic motion, and then what we get is a wave that has a period, it has a frequency, it has an amplitude, and it also has a wave speed, which we'll talk about in the next section. And if it's a one-dimensional wave, that's again 1 point on it. It talks a little bit about what happens. This is the equation. You end up with something that is the disturbance is a function of x and time. And it's the cosine of 2 pi over t times minus x over v. So the variables here are y, lowercase t, and x. And the constants are the amplitude of that wave, the period of the wave, and the speed of the wave. So that's a, capital T, and v are the constants which describe that particular wave. And then you can also derive something called the wavelength. This is a Greek letter lambda, which is the period times the speed, or also the speed over the frequency. And you can think of the wavelength as the distance that the wave propagates during one period. So remember delta x equals v times delta t, so the wavelength is the period t times the speed of the wave. It's also equal to the distance between two nearest points in a wave, like the two crests on the wave will also be the wavelength. So here is another way of writing that. You can now use wavelength as another way of describing the wave. So you've got amplitude, period, and wavelength. And here again is y as a function of lowercase t time and x. They talk a little bit about snapshot versus history graphs, making sense of what looks like for a longitudinal wave in which you've got displacement from equilibrium versus its position. There's definitely a lot to read today, but section 11.3, the last section, is on wave speed. So I told you we'd be coming back to that. So what determines the speed of a wave? Well, it turns out that it's the properties of the medium in which the wave travels which determine how fast waves travel. So they go through this observation experiment. If you change different things about the wave, change its amplitude, change its frequency, change the force on the spring, or the length of the spring, and then look at the different speeds. So what's interesting is that when you change that force, the tension in the spring or in the string, that's the only thing that changes the speed. All these other changes in the amplitude or the frequency doesn't change the speed of waves on a slinky. So it's somehow proportional to the square root of that force. And so there is a derivation here. It turns out the wave speed, here in equation 11.5, is the force, so the tension in the string, divided by mu, where mu is the mass per unit length. Not to be confused with the coefficient of friction from previous chapters, but it's the mass per length, kilograms per meter, of the string. So that's useful if you're talking about the wavelength of a wave that's on a string. You need to know the speed. The speed is going to be that force, the tension force, divided by the mass per unit length. And that's it for the reading for today. I'll see you next time. Bye.